Every time you use Google Maps, something invisible happens. A signal leaves your phone, travels to a satellite 20,000 kilometers above the Earth, bounces back, and your position is calculated to within a few meters. That calculation depends on timing, incredibly precise timing. The kind of timing where being off by even 1 microsecond, 1/1,000,000th of a second, puts you in the wrong building, on the wrong street, possibly in the wrong city. The technology that makes that possible is not in your phone. It is not in the satellite. It is in a room, in a government laboratory, where a machine counts the vibrations of a single cesium atom, 9,192,631,770 times per second, and uses that number to define what 1 second actually is. You have never seen it. You will never need to think about it. But without it, the modern world as you know it stops working. Immediately. For centuries, the rhythm of daily life was set by the turning of the earth. Noon meant the sun at its highest point, and every second was a fraction, 1/86,400th of the average day. This was the mean solar second, carved out of the planet's rotation. But the earth is not a perfect clock. Its spin drifts, slowed by the tug of the moon, nudged by shifting winds, and even wobbled by movements deep within its core. Over years and decades, the length of a day can change by milliseconds, tiny on a human scale, but enough to throw off calculations that demand unwavering precision. The planet's motion, once the ultimate authority, proved to be an unreliable keeper of time. A world that ran on rough time could tolerate the drift of the planet. A few seconds off meant little to a farmer or a town clock. But at sea, 4 seconds of error spelled disaster. A ship's position could be wrong by a mile, enough to run aground or vanish in the fog. As the 20th century advanced, the margin for error collapsed. Radio broadcasters needed to synchronize programs across continents. Radar demanded pulses timed to millionths of a second to track bombers and guide artillery. Nuclear research called for even finer control, chasing particles in microsecond bursts. The old, uneven second, shaped by a restless Earth, no longer met the needs of science or safety. The question sharpened. Could nature itself offer a frequency more stable than the turning of the world? Louis Essen worked in the quiet corridors of the National Physical Laboratory at Teddington, far from the glare of public attention. With Jack Perry at his side, Essen set out to do what no one had managed before. Build a clock that would measure time not by the drifting spin of the Earth, but by the unwavering regularity of the cesium-133 atom. In 1955, their machine took shape, a wardrobe-sized assembly of vacuum tubes, magnetic shields, and electronics, humming with hidden purpose. The result was astonishing. The clock lost only about 1 second every 300 years, an accuracy of 1 part in 10 billion. Where the old world measured days by the sky, Essen's clock found the rhythm of the universe inside a single atom. He was a man of sharp intellect and fierce conviction, so confident in his work that he would later challenge even Einstein's theory of relativity. Yet whatever his disputes, the cesium clock stood as proof. Time could now be counted with a steadiness the Earth itself could not match. Inside every cesium-133 atom, a hidden rhythm pulses with perfect regularity. When exposed to a carefully tuned microwave field, the atom flips between 2 energy states, like a switch thrown back and forth, again and again. This flip is no accident of chemistry or chance. It happens at a frequency that never changes. It is 9,192,631,770 times each second. Not one more, not one less. That number is not a matter of human convention. It is written into the fabric of nature itself, a code as universal as gravity or the speed of light. By the mid-20th century, scientists realized they could use this atomic rhythm as the anchor for all timekeeping. The cesium clock built by Essen and Perry was proof. No drift, no wobble. Just the unwavering tick of the atom. In 1967, the world's timekeepers gathered in Paris and rewrote the definition of the second. The old solar second, tied to the drifting spin of the Earth, was replaced. 1 second became the time it takes for 9,192,631,770 oscillations of microwave energy to drive a cesium-133 atom from one state to another. The second was no longer something we measured by the sky. It was something we discovered in matter itself. All the clocks, all the satellites, all the networks, every heartbeat of the digital world now rests on this invisible atomic drumbeat. Subscribe for more stories that reveal the hidden machinery of our world. Every time a phone checks its location, it listens for signals from satellites orbiting 20,000 kilometers overhead. Each satellite carries an atomic clock, ticking out the cesium rhythm set by the same quantum pulse that defines the world's second. On the ground, master stations compare and calibrate these clocks, correcting the tiniest drift. When your phone calculates its position, it's not reading a map. It's measuring the arrival times of radio pulses from space, comparing differences as small as 20 nanoseconds. At the speed of light, 20 nanoseconds is 6 meters, the width of a city street. A single microsecond of error, just 1/1,000,000th of a second, can shift your position by 300 meters, enough to place you on the wrong building or across the river. If the atomic clocks on the satellites were switched off, GPS would begin to unravel within hours. The system would lose its grip on time, and with it, the power to navigate the world. Subscribe for more stories that reveal the hidden machinery of our world. The invisible pulse of atomic time now runs through every corner of digital life. Each internet transaction, each email, each login is anchored by synchronized timestamps that trace back to atomic clocks. In financial markets, microsecond-level timestamps decide the order of trades, settle disputes, and power audits that span continents. The electricity grid, humming at 50 or 60 hertz, depends on atomic time to keep alternating current in phase across thousands of miles. Mobile networks hand off calls and data between towers in perfect sequence, guided by the same atomic rhythm. What began as a wardrobe-sized machine has been miniaturized onto microchips, shrinking from laboratory cabinets to devices smaller than a coin. The standard that once belonged only to national labs now underwrites the ordinary everywhere. Every search, every signal, every global step, balanced on 9,192,631,770 atomic oscillations each second. Civilization now runs not on the turning Earth, but on the heartbeat of matter itself. Subscribe for more.